Okay, so we'll be beginning the first session, and I'd like to introduce Mateusz Kwiatkowski. He will be presenting effective debugging of embedded C.
Hello everyone, my name is Mateusz Kwiatkowski. As Mieszko said, I'm a senior software engineer at the embedded team here at AVSystem. And I'll be talking a bit about effective debugging of embedded C. So first of all, why do we need debugging? This is because, like you know, the old Murphy's Law, anything that can go wrong will go wrong, but we cannot just live with it. We cannot just tell our bosses and customers and users that our software will never work. So we need to do something about it. I will start by talking a little bit about things you probably already know about debugging. But first of all, I'll introduce you to this little snippet of code, which has a bug in it. But some of the more inclined of you might say that there is actually a lot of wrong things with this code. For example, stringifying a floating point number is maybe not something you should be doing yourself. Maybe you should use printf or something else from the standard library. Also, you have this division by 10, which loses floating point precision, obviously. And also there is a recursive call here, which is a big no-no in some embedded situations. But those are some compromises that sometimes have to be made. So this is actually not the point. This is actually not the bug that we are looking for. The bug that we are looking for is that, well, of course, it works if we pass 1.5 E6. This is what is supposed to be output. But 10.0, this is not really how the exponential notation works. Also, we wanted it to start with exponent of 6, but it doesn't. So you probably already see that this one should be greater or equal, and this one should be greater or equal as well. But how do we get there? Of course, the first method of debugging that you probably learn is debugging using printf. So you put some not really nice words in your code that are output to the console, and you see those not very nice words telling you where the code is being executed and what values are there, and you can reason, for example, that in this case we are not entering this loop, and for the 1E6 variant you just got one message, so you can see that even this if isn't triggered, right? But there are, of course, many problems with this approach. We need to put strings somewhere, and in embedded, we often don't really have much place in the flash memory to put all the strings. Also, we need a standard I/O or something like that, which is especially this is especially problematic in this case because we are re-implementing printf. Basically, we are implementing outputting the floating point number. So we need to output floating point number. This is a little bit of a chicken and egg problem in this case, but also we need to output this somewhere. We need a serial port or a monitor or something like that. Of course, we probably have a serial port of some kind, but there are race conditions. For example, if we are outputting something else on the serial port, then putting more logs might cause some other problems. So another thing you probably know how to use is a debugger, like GDB on this, let's call it a screenshot. So using a debugger like GDB or LLDB that you can use from the command line, or in GUI you can use something like Visual Studio or IR. Many IDEs have debuggers integrated. Other IDEs are wrappers around command line debuggers, like you can use in VS Code or Eclipse or CLion. And using the debugger, you can do stuff like single stepping, like execute one line of code at a time. You can put breakpoints so that execution stops when you reach some point in the code. You can use watch points so you can see that when a variable changes, then the execution will stop. You can also print values of variables in the command line or in a window. You can even modify them. You can do disassembly. Basically, debuggers are very, very neat, very nice tool. But we are working with embedded, so we've got a couple of problems, obviously. To get the code to fit on our device, we probably need to turn on optimizations, and if you ever trace through optimized code, then you know that it is an experience. And also, we need to know about the limitations of embedded hardware, because we can have a limited number of breakpoints, so we are not able to just use them as we want. Watch points may not even work or behave weirdly. And we need a debug probe. Some development boards usually have them included on the board, but if we have something other than a development board, then sometimes we can get away with using another device of the same kind, like with the Raspberry Pi Pico. But if we have a really production device, then we need an external probe, and something like this nice J-Link costs 400 euros, which is interesting. Some other probes are a little bit cheaper, but basically we have a lot of problems, and if that even weren't enough, then there are other limitations. For example, production devices may have if uses that disable the ability to be debugged at all, or we can have secure code like ARM Trust Zone, where also by design you cannot debug that code using a debug probe. So if we are developing code for the secure enclave, then we need to somehow get around that. And if that wasn't enough in itself, then we have the kind of bugs that other developers don't even know. Like we may have unaligned accesses that don't crash the code, but just do something very weird. We may have bugs in our RTOS. So, for example, we once had a bug that caused the stack to go totally out of alignment, but only if you were passing a 64-bit integer or floating point value through an ellipsis, like a printf. So you have very sneaky bugs sometimes. If you have wrong settings for your compiler, then you can have race condition in the function preamble. That also happened in real life, and you can read about that on the blog article that is linked on this slide. And sometimes vendors provide you with some drivers with C code, but it only works when optimizations are disabled. You can have problems with caches and DMAs and all very interesting stuff. So what do we do about it? Well, I have some tips for you to make your debugging experience hopefully a little bit easier. I'll start with a little tip that doesn't really have much to do with embedded development, but I really encourage every one of you to learn how to use GDB from the command line. This is because, first of all, it's not that hard, and you can have things like GDB's integrated TUI to ease the learning curve. There are also things like GDB dashboard. But when you use GDB from the command line, you can effortlessly integrate with external tools that build on top of GDB, like Valgrind or RR, which we will talk about a little bit later. Also, GDB can be extended with scripting, with Python modules and so on. You can write them yourself to, for example, examine your custom data structures, things like that. So really using GDB from the command line instead of GUI is really worth it, in my opinion. You can even do a little bit ad hoc scripting. For example, if you create a breakpoint and then type commands, then you can type a list of commands that will be executed when that breakpoint hits. So this is something that I really did in real life when I had a really sneaky bug. In fact, when debugging this race condition generated by the compiler. I was just basically single-stepping through the code, but automatically. And I didn't really know where to put the breakpoint, but I wrote a little ad hoc script that checked when the memory corruption happened. And that is the way I caught the bug in the end. Also, when watch points don't work, then yeah, you can do that to emulate watch points. You can basically single step in a loop and see if the value changed. Another tip is that, like I said, watch points don't often really work on embedded. Part of that is because if you type watch some variable in GDB, then it will actually try to evaluate it everywhere, but you might be in another function and there is no such variable anymore. There is watch -L, which is supposed to watch a specific location in memory, but I tried to use it and it didn't actually work for some reason. So what always works is if you have a variable, you can take its address and put an asterisk before it and watch that. It might not look pretty, but it works and it never failed me. Yeah, but you also may do that to, for example, if you put a watch point and reboot the board, then it will also be triggered when the memory is initialized. You have this startup script, which is assembly script, and basically zeroes out all the data section in the memory, and you will also get that watch point triggered then. You will also get it triggered when the operating system initializes some memory and so on. One more thing that is very much, maybe not necessary, but comes in very handy, is learning how to read assembly. You probably don't need to write anything in assembly, but being able to understand a little bit of that really helps. For example, you can single step on the assembly level, on the machine instruction level, instead of single stepping through compiled through C code, which may actually be helpful and may actually be more easy to understand when you are debugging through optimized code. You can use, for example, godbolt.org compiler explorer to correlate what is happening in the code with what is happening in the machine code, because that tool helpfully provides some color coding between lines of both versions of the same routine. To do something in the other direction, you can use one of the better things that came from the total privacy violations of American NSA. You can use Ghidra. This is a very powerful tool for decompiling and disassembling and analyzing binary software. Of course, you should probably check with legal if such reverse engineering is allowed, or don't tell anybody about you doing it. But you can feed it with some binary application, and it will try its best to get something that resembles C code with the same semantics. Sometimes it does really well, sometimes it does meh, but you can at least get an idea of what is going on in the assembly code, and this can be used, for example, if you have some bootloader. You may even have source code for it, but you don't know what exact compile options have been used when compiling it, and many software is totally configurable at compile time. So if you don't know which options were used to compile the version you have, you can just decompile it and see what is going on. Another thing that comes really handy is instrumentation. Instrumentation is basically when you have the compiler insert code in your application for you automatically. There are many different use cases for instrumentations. For example, you have Google sanitizers like address sanitizer, threat sanitizer, and so on, which put some checks in your code to check if you are violating memory or doing undefined behaviors and so on. You can have control flow protection, which is actually enabled by default on modern Linux, and it checks whether you are jumping to a valid address or not. You can have a stack protector, which is some rudimentary protection about buffer overflows. But the thing I want to talk about is F-instrument functions. This is a very powerful tool, actually. You need to declare two functions with some really funky names like sigprofile func enter and sigprofile func exit. And when you do that and put some also funky flags on the compiler command line, GCC helpfully has this functions exclude list, so those two functions don't get instrumented as well. Otherwise, we would have an infinite recursive loop. And when you do that, those functions are executed on every entry and exit from every function in your code, which can be poor man's printf, automated printf debugging, basically. You can see where the code is being executed. If you have synchronous output on the serial port, for example, you can also see what is the last function that is being executed, which can be really helpful. This also works on Clang. However, on Clang, you need to put those two functions in a separate translation unit, because there is no exclude list, so we need to compile that separately without the F-instrument functions flag, but otherwise it works the same. One thing that Clang has that GCC doesn't is that you can also use F-instrument functions after inlining, and in that version you don't have those calls for inline functions. If a function got inlined, then calls to, well, this is not really a call on the assembly level, but only proper assembly level function calls are instrumented in this way, which I don't really know why you might prefer that, but you may. Of course, there are some advantages and some limitations of using this. It works everywhere, but you still need some kind of output, but it may come in handy when you are debugging code that runs inside a trust zone, for example. It has low overhead, aside from the fact that, well, of course, you need output of some kind. And combined with manual printf debugging, that it can be really powerful. But there are, of course, other limitations. You need to correlate the addresses that get printed out with your code. You can do that using GDB or Gitra or something, but it will be tedious. You don't have access to variable values. And it is not really that... I said that you can correlate the last function that gets executed, but this is not always true. If you have, for example, asynchronous I/O, then the thing you want to output on the serial port might just get buffered, and then your port will reboot before the buffer gets printed out. So this is not 100% always working solution, but this is still really powerful. That can be helpful in many situations, especially when you don't have a possibility to use a proper debugger. One more thing I want to encourage you to use is Linux, or you know how this goes. This of course does not apply to your target board, but your development machine. And why you should use Linux. Let's see a couple of tools that you can use in C and C++ development. I already talked about GDB. That works on pretty much everything. There are sanitizers, and those are limited to GCC and Clang, but that also works pretty much everywhere. but not on an embedded usually, because you need a runtime that is relatively heavy and probably won't fit on your board. There is scan build, which is used for static analysis of your code. This is also part of the LLVM package, so it works mostly everywhere. But things like strace, for example, or ltrace, those are Linux only, although to be fair, BSD and macOS folks also have dtrace, and Windows is process monitor, so there are equivalents on other places. But Valgrind doesn't work on modern macOS, for example. It only works on Linux and a couple of other Unix-like systems. RR works only on Linux and is finicky with virtual machines. So you have a lot of tooling on pretty much every platform you can have, but if there are some tools that only work on one platform, then probably that will be Linux, at least if we are talking about the open source ecosystem, because maybe you can have some tools from Microsoft or something, but who uses Visual Studio anymore? Anyway, why does this matter? We are talking about embedded, right? Right, but if you can run at least some of your code on your computer and not just on your target board, you probably should, because it opens up a lot of more possibilities for testing and debugging it. Some platforms even allow it to be done very easily. For example, on Zephyr, you can target a native SIM board, which compiles your program to a normal Linux process. And this is also a thing that only works on Linux. You cannot do this on macOS or BSD or anything like that. Of course, you cannot test your drivers there. You may be limited in the choice of libc that you are using to your native libc of your system, but still this is your embedded code running on your computer. If you don't use Zephyr, then you probably need to roll your own, like you can just take parts of your code and compile it as a separate application. But this is worth it. This is definitely worth it. You should do that as much as possible to test your code, to debug your code, because it allows you to use a lot of more tooling and free yourself from the resource limitations of your embedded board. So what you can do? I already talked about address sanitizer. This is something that you enable on the command line of your Clang or GCC compiler. And when you enable that, when your program tries to access some memory address that is invalid or leaks memory, you will have it nicely printed out on the console, and some error code will be returned. This is very handy. However, there are other sanitizer. For example, there's memory sanitizer that I forgot what it does. Memory sanitizer, I think it checks if you are using the right section of memory, something like that. Anyway, you cannot use it together with other sanitizer, so you cannot enable all the sanitizers at the same time. Another handy one is undefined behavior sanitizer, which, as the name suggests, will try to alert you when you are trying to do some kinds of undefined behavior in your program. For example, in this example, you are doing signed integer overflow, and this is printed as a runtime error. Like I said, there is also thread sanitizer, which checks for race conditions in your code. For example, if you have different order of locking mutexes, it will alert you about that. And there is memory sanitizer, and I finally have notes for that, and it checks if you are using uninitialized memory, not just invalid address, but you have a valid address, but you didn't initialize it, and it will warn you about it. Of course, there are limitations. It relies on compile time instrumentation, which is very handy, but if you have an external library which is binary only or something like that, then you will need to recompile it, or if you can't, then you are screwed. And it only catches a subset of bugs. Famously, C++, not C, but C++ has a rule that if you have an endless loop, without a body. So you have a code that does nothing, and you try to hang your program with that. This is illegal. This is undefined behavior, and compilers are free to optimize it. So if you put while true semicolon and enable optimizations, it will be removed from your code, and the code that is below it will be executed. But undefined behavior sanitizer doesn't find that bug. So yeah, you cannot 100% rely on it. And also, even worse, if a bug is even able to be caught by, for example, undefined behavior sanitizer or address sanitizer, if you have, for example, unaligned memory access, but possible unaligned memory access, but you just so happen to calculate an address that by chance happens to be aligned, this will not be caught. You need to have an actual bug in runtime for it to be caught. This is what I was talking about. So one way to minimize the risk of you forgetting about some bugs is, of course, have a lot of tests and high coverage of your code with automated tests. And of course, you can always have false positives, and with Google Sanitizer, this is a little bit hard to manage because you can only configure those using environment variables, which is rather tedious. So, introducing Valgrind. Valgrind does a lot of the same thing that Address Sanitizer does. It can catch things like invalid memory accesses, heap usage problems, memory leaks, and so on, and other things, because this is just one of the tools of Valgrind. There are other tools. Instead of memcheck, you can use Hellgrind, which checks for race conditions. You can use call grind and cache grind, which analyze your function call trees and so on. But memcheck does more or less the same thing as Address Sanitizer, but it does it on unmodified binaries. So it does just-in-time instrumentation of binary code and analyzes that. Like I said, there are other tools, like you can use cache grind and call grind to profile your code basically and see what calls where. You can use massive if you are using heap, which you probably don't on embedded, but if you do, then you can see a plot of heap usage and what allocates how much memory and so on. Like I said, Valgrind has the advantage that you can just test anything with it. You can test release binaries, external libraries, and so on. And it's highly configurable. And if you are testing your own code, then you can use Valgrind's library to mark, for example, you can put something like this, and it will not treat a variable as undefined, even if it would otherwise. But of course, the code will be slow. You got like 8 times slower execution of the code because it basically runs something like a virtual machine to emulate all your code. So there is a significant performance impact. And again, it only catches a subset of bugs, only when they happen, and so on. Because it doesn't understand your code, your C code, it only understands binary compiled code, then it has no concept of type checking, for example. And it can crash in some situations. For example, I tried, because famously, I think it is used in some quite large projects, so I tried running Firefox under Valgrind, but it crashed because it couldn't cope with cloning Linux processes and so on. So in some situations it might not work, but usually it does, and when you try different approaches at the same time, then you can get very good results. Another thing you might consider using is scan build. This is static analyzer for your code. You basically put scan build before your make or CMake or whatever you are using, and it will generate a report when it sees some suspicious code. And RR, this is, I think this is the last thing I have on the agenda. Yeah, sorry about this doing that. RR is a tool originally developed at Mozilla. One problem with it is that you need some very specific hardware to do it. If you have an Intel processor, then it basically works. But if you have AMD, well, it needs to be relatively new, or even newer ARM processor, like probably Raspberry Pi 5 is okay, but anything earlier than that won't work. It will work on an M1 Mac, but only if you boot Linux natively, so yeah, a little bit problematic, but when you get it to work, also doesn't like virtual machines. But when you get it to work, on this here you can see that you can record execution of your application and then type RR replay. This looks just like a normal GDB session, except when you hit some problem. You can do things like reverse next and just go back in time with execution of your code, put a breakpoint and do reverse continue and just replay what happened to create the bug again. How does it work? When you record your application, it virtualizes anything that can be non-deterministic about your program execution. This has some CPU overhead, but not really that much, about 20%. And when you replay, it doesn't do those system calls, for example. It doesn't really do them. Instead, it injects the result from the original execution. So if you have a network application, for example, during the replay, it doesn't access the network. It just behaves as if the receive call received the same data as it did in the original run. So you can basically record some problem and then replay it multiple times deterministically as if the program was running live using debugging, and you can do reverse execution as well. But you cannot generally move it to other machines. This is really much tied into the CPU type and so on. So as long as you're on the same computer, it will work, but otherwise, not necessarily. As a side note, GDB can also do this, at least in theory, because when I tried doing that, it didn't do much. So I would recommend sticking to RR, at least for the time being. So, those are some tools that I recommend you using, some tips on debugging your C code in embedded, but also in other contexts. This is everything from me. If you have any questions, then this is the time to ask them. And if you want access to this presentation, then you can scan this QR code. So, are there any questions? Sure.
Thanks for the presentation. I wrote down a few questions. In fact, first, how you recommend to find a bug which appeared when we turn on optimization or increased optimization level and just stop work?
That is a bit tricky. I think there isn't really much you can do other than tracing through optimized code on the assembly level. Or maybe you can try analyzing it using Ghidra or something like that, and just see if you see anything suspicious in the resulting code. But yeah, if something stops working when you enable optimizations, then you can either just spend a lot of time searching for what you did wrong, or you can just disable optimizations for that function, which is what we ended up doing when we had that problem with drivers. This is another thing, that this wasn't our code. This was a code from a hardware vendor, some drivers, and we found out that those are written in such a way that you cannot enable optimizations. So we just disabled them for this code.
And second similar question, I have a bug, so I add print to find out what's going on, and bug disappeared.
Yeah, that also happens sometimes. What can you do about it? Static analysis sometimes helps, because if you have bugs like that, then this is probably some kind of undefined behavior or some kind of a race condition. So it can sometimes be caught using static analysis. It can sometimes be caught by running your code under thread sanitizer maybe, or Valgrind using the Hellgrind tool. But yeah, this is hard. I shown you some tips, but I don't have answer for everything.
Okay, and last question, maybe not directly related, but somehow. What kind of test framework do you recommend? Google Test or something else?
This is a little bit tricky question, because actually here at AVSystem we have our own.
Okay.
It is actually open source. You can go to our GitHub and see a project called AVS Commons, and there is a framework, AVS Unit, as part of the AVS Commons repo. But at the end of the day, it doesn't really matter that much. You can use gtest or whatever feels comfortable for you. Or I have seen many open source projects just writing plain old applications that just execute some code and then do old style, just plain C asserts on the results. So the test framework is really there only to help you write the code and maybe make it a little bit comfortable executing it, but it doesn't really matter that much.
Do you see benefit of having some hardware in the loop simulators as well?
Could you repeat?
Do you see a big benefit of having hardware in the loop simulators, or you are not using such facility when you have your hardware, real hardware, connected to some extra test bench just to run set of unit and integration tests on that?
If you can fit the unit and integration tests on your hardware, if you don't have problems with resources, either just a place on the flash memory or RAM, or it may also be the lack of an additional serial port or something like that, then of course that is also an option. That is even a better option, because you are testing on the target hardware, of course. But testing on a simulator or just as a plain desktop application has some benefits as well, because it is easier to do debugging. You can also just run those tests quicker, more frequently. So I guess the best idea is to just combine both if you can.
Thanks.
Are there any more questions?
Okay, thank you so much.
Thank you. Oh.
And we'll be back in 3 minutes for the next session. Okay, so for the next session, we have Yury Samusevich and business analysis in IoT project. So welcome. Let's begin.
Hi everyone, my name is Yury. I work as business and project manager at the company. Our company is specialized in development different IoT solutions, mostly the development of things. And I would like to tell you about non-engineering part of our work, about business analysis. Just to remind one about what it is, business analysis. The practice of enabling change in an organizational context by defining needs and recommending solutions that deliver value to stakeholders. The definition according to BA book is the main book for many of business analysts. I think that you know the definition of the IoT, and we can move forward and to speak about the role of business analyst. You know that projects could have business analysts or system analysts or anyone else who is responsible for keeping updated the project requirements. Sometimes engineers also work as business analysts or do business analysis, not even understanding it. I have to tell that it is not an obligatory role, and mostly business analysts identify and define solutions that will maximize the delivered value to the project. We have to figure out business needs of different companies, for example, or future probable solutions. It's important to attract funds and investments. We usually are working on several fields, like, for example, market analysis, technical feasibility study, study of data. We are working with hardware, understanding what the product should consist of, and so on. Also, we can recommend software and platforms for future solutions, and elicit requirements about security level and so on. The next, the first layer. Okay, we have an idea and we have to understand our condition. We have to think of our future target audience, and there are different tools how to do it, how to analyze customer expectations. Usually different analysts use such techniques as SWOT analysis when we figure out future project strengths and weaknesses, try to find opportunities, and also to find all possible risks and threats of our product. Sometimes it's a good idea to analyze probable competitors and, for example, to compare existing solutions, to create a spreadsheet when we enter the information of the current cost of core features of the product. It's important to understand what should we bring new to the market, and what features our product should have to find our target audience, to analyze market trends. But for more comprehensive and for deeper market analysis, it's a good idea to hire market specialists. They have also different tools, and they can do this work better. Okay. When we have a good idea, when we identify business needs, we have to start our work, and the good idea to do it not just from for example, coding, yeah, but it's a good idea to start the project from the discovery. It also could be called like a technical feasibility study. During this phase, it's important for business analysts to elicit different kind of requirements about the software network, about security, data. Usually we split all of these requirements into two groups, functional and non-functional requirements. The functional requirements answer the question, what product do and how, and the non-functional requirements answer the question how it works. During the discovery phase, we also can figure out, for example, the probable cost of future solution of the device. What price could we offer to our possible clients, and even to understand whether we need to develop this product or have to stop the development on this phase, not to spend money and time for useless device, for example, or for useless solution. Usually we could decompose all the tasks into during this phase into to figure out, for example, what epics, stories, and subtasks the future work will have, to estimate this task, to understand how much time it will take, and it is information for marketing departments and for our investors, for example, to know how it is difficult to develop the product, and how much time it will take, how much money it's necessary to spend on this idea, and so on. Okay, when we finished the discovery phase, or during the discovery phase, so we pay much attention to the data. You know that data is a significant part of work for all of IoT projects, because sometimes the data that sensors collect become the core feature of our solution, and it's important also to think of the tools that we should use for the collecting of this data. The data life cycle in IoT projects sometimes could be very complicated, because data exists on all of levels, from hardware, in application, in services, and we have to answer on questions, for example, how we process this data. Should we use different amplifiers, filters on the hardware level? Then how do we transmit this data to our applications, if we use these applications? Sometimes we have different databases on all of this level, in the firmware level, in software, and in clouds, and we have to estimate all of these connections. It's a good practice to prepare special diagrams like entity relationship diagram when we figure out, for example, all of these dependencies and characteristics of variables. Okay, when we have a good list of requirements, we know all our probable features, we also think about our hardware level. During this part of work, usually mechanical designers and different engineers, PCB engineers, also take active part in our work, And we have business analysts, we have to supply them with all these requirements. They have to know all the features that we develop and to decide what approach we use, because on the hardware level it's crucial to solve, for example, some basic issues. You know that, for example, power supply, power management takes could be quite difficult, and we have to decide, for example, and to know whether we have the access to electricity grid, or we have to use rechargeable, replaceable batteries, or something else, for example, solar power. And usually we create a list of questions, something like a questionnaires, and discuss during our workshops and in the meetings with our customers, and answer all these questions. It's important to keep in mind all of this information during the hardware design. Sometimes quite easy questions from the first glance could cause difficult, for example, discussions. Such questions like whether we need to enable a button in our solution or not. It's simple question, but this small element could solve many issues, for example, in the future. And also it's important to prioritize, especially in the discovery phase, for example, what features we should do firstly, what should be included in our MVP product, what can we add to the second iteration or remove from the first prototype. Also, usually we describe how the data will be visualized, whether we need to enable displays in our device, or we use external tools to visualize this data, we use applications and so on. It's important to pay much attention to enclosure design. Usually it's a good practice to attract a specialist, the designers who prepare different sketches, for example 5 or 7 sketches of prototypes, and to offer this solution for customer, or just to choose appropriate one between us in team of developers, and so on. Okay, let's continue. When we understand how our device looks like, what enclosure we use, what materials we use, what components will be included in our device, business analyst could also offer different software and other services that could be used for our solution. Firstly, we have to decide whether we need, for example, mobile application. What operational system will be used in our solution, Android or iOS? It's quite a simple question from the first glance, but also market analysis could help us to answer on this question and to understand what is the target audience, what applications they use, what devices they use to run our solution. Sometimes it's better to know, for example, how much the future services will be cost, and analyze different tariff policies to know what is the price of future project or product maintenance. It's also a good idea to create a comparative table and spreadsheet, in this spreadsheet to figure out to write all, for example, advantages and disadvantages of different services that we are going to enable in our solution. Let's talk about security. You know that sometimes we think that our devices or IoT solutions have many weak zones, and the data could be stolen, and we have to understand, for example, do we need different security protocols to encrypt our data? How should we store this data to understand the policy of data access? What groups will we have to get access to this data? How this data and groups will be managed, and who is responsible for administering this data, and so on. And also future products could have different other risks, not only concerning, for example, access to the data, but other business risks. And it's a good practice to have risk register when all of these risks are estimated, have a scale, for example, from 1 to 5, and when we can figure out, for example, what should we do to mitigate this risk or to remove. Sometimes after the launch, the MVP version, for example, we see that we don't have issues with risk A, but we see, for example, a new risk, and it's important to keep this document updated and actualize it. Okay. What tools we use for our work? I think that most of you know all of these tools, ordinary tools that managers use in their practice. It's important to choose the platforms when all these documents, because I told about documents that business analysts create and how we store this data. For example, in my practice, I usually use Confluence or some other clouds and drives. How we can manage all the tickets and tasks, and usually, for example, in Jira we describe the future task. Also, knowing the dependencies between tasks, for example, A and B, we can also point it and to leave a special comments and this tool. For better business logic description and feature description, we usually use diagrams, and these diagrams visualized in form of different charts, for example, UML diagrams or BPMN, and different collaboration platforms for communication. For different projects, we could create, or for different teams, special channels when we also have a special rule how to leave the comments, how to share the ideas, and so on. Usually business analyst is responsible for prototyping, and you use different tools like Figma or 3D models, or application for 3D models, and for future mobile applications we can just to write screens, not beautiful pictures, but to understand, for example, what buttons, what menus the screen A will have, and so on. And this information is important for our project estimation, to understand the complexity of the work as well, and it helps engineers to estimate the work and to understand how much time they have to spend on this feature implementation. Also, I would like to tell you about my experience. For example, in my project, I use different methodology. For example, for application development, it's a good idea to work sprints according to Scrum guide. For hardware development, I usually use Kanban. In my practice, it's a good idea to create, not for every project, it depends on the complexity, on the amount of team members and so on, a different document, the vision and scope. Sometimes it's just a simple feature list with the description of all of these features. For more complicated tasks, for more complicated features, it's also a good practice to draw diagrams and to use and to describe a use case. Also we have to have a plan, something like a roadmap, when we know, for example, what should we do firstly. We develop hardware, and then we go to the firmware, or we synchronize all of this work. So for better process establishment, it's important to organize cross-functional collaborations between all of teams, between hardware engineers, software engineers, to schedule their work and to get a feedback. During the project estimation, during the task estimation, it's also quite important to attract all of these engineers to this work, to listen to them, because sometimes they have more information and practice, and can recommend, for example, what components we have to enable in our devices and what services we should use according to their practice, and so on. Thank you for your time. Do you have any questions? No. Thank you. Okay, you're welcome.
What would be the difference between business analyst in IoT project and a business analyst in some kind of other project which doesn't involve IoT? So let's say if you're building a social media platform,
Okay.
I think you still need to go through all of those things. So what would be the difference?
In practice, the difference that we work close with hardware, and sometimes it's important to be ready to elicit requirements for hardware, to offer something, for example, for investors, for those who is responsible for future project development, and working with special, for example, IoT services as well becomes a feature, but there is no dedicated discipline. I know that my colleagues from BA community can specialize in different fields, like, for example, in fintech or in healthcare domain, and a special discipline doesn't. Okay. Okay.
In Scrum methodology, how does the cooperation between BA and product owner looks? Because I see some common task, let's say.
You know that according to the Scrum guide, there is no a role of business analyst. There is a role of product owner and engineers, and the business analysts work like a QA, for example, engineers, in team of engineers. But in practice, he just help product owner and offer solutions according to his practice, according to previous practice from other projects.
There are no conflicts between these two roles?
What?
There are no conflicts between these two roles?
No, no conflict. Yeah.
Okay, so thank you so much, and
Thank you.
and we'll have a 10 minutes break. Okay, so we'll be starting with the third session, and we have Piotr Wilkoń with us. We'll be presenting the embedded subsystem in Narwhal, so underwater ROV. ROV.
Hello everyone, my name is Piotr Wilkoń and I am the embedded team leader in AGH Marine Student Club, and today I would like to talk about the embedded system in our new project, the underwater remotely operated vehicle Narwhal. So let me introduce our club and our team. Our club was established in 2018 by then students of the AGH University. Since they were in the same age, they simultaneously graduated in 2022. So the new version of our club began in 2022. The main field of work in our club is the underwater robotics. So we basically built underwater stuff, mainly the vehicles. We reorganized everything in 2022. We conducted a few recrutations and we gathered around 30 members. These are people of different ages, from different fields of study, the electronics, mechanics, ICT, and others. We had some smaller projects during the period of activity of our club, but the two notable projects were the remotely operated vehicle Gupik and the autonomous underwater vehicle Haller, which is shown here. Now we are working on our new project, the remotely operated vehicle Narwhal, that we want to show and attend we want to attend the Mate ROV competition, which is held in July 2024 in Tennessee, US. So I hope that we can do that. So I told you about that we had ROVs and AUVs. But what does it actually mean? So we have let's start with the AUVs. These are the autonomous underwater vehicles. These are the vehicles that have little to no connectivity with the ground station, with the station on the surface. They basically operate by themselves. They have some AI algorithms built in. So they have also some sensors, some cameras, and they have some tasks programmed in first, of course. There is an operator, a programmer that programs some tasks, some initial input to the robot, then the robot is thrown into the water and it must do the tasks by itself completely. And we must hope that it will return to the surface. These robots have no means of communication, not wireless nor wired, so they are usually also battery operated, because their main purpose is to explore very inaccessible areas or very deep sea or some caves or the areas that are dangerous to humans. So we would rather avoid having any kind of wires because it would limit the range, and when we have wires, the range is usually limited to like 20 or 30 meters. The obvious drawback is that the batteries have limited capacity, and such robot must do its tasks in 20 or 30 or 40 minutes, and then it must return because the thrusters consume a lot of power. On the other hand, we have the ROVs, the remotely operated vehicle, and Narwhal is one of them. These are the complete opposite of the AUVs. They have a constant connection with the surface. It's almost always a wired connection. They are fully controlled by the operator, so they have some camera on board, which is the most important thing, that is a feedback for the operator. And there is some control station on the surface. Since they have some mean of communication with the control station, there is also power supplied through a cable from the surface. So the ROVs don't suffer from the problem of AUVs, which is the limited battery capacity, because we have some PSU on the surface, and we can work with them, we can use them as long as we want. So here we have a very general model of our robot. We have our Narwhal and control station with a power supply. And I told you that for ROVs the RF is practically unusable, and we must use wired connections. And why is that? Because the attenuation of the radio waves underwater is actually huge, and we can't use any kind of protocols you would normally use to connect with any device on even a few megahertz, not to say anything about Bluetooth or Wi-Fi that work on gigahertz. The actual range that works under the water are the very low frequencies, but the very long frequencies imply very long waves, and very long waves require big antennas, and since the robot is very small, we can't have big antennas there, and we would need small antennas. But the problem is that small antennas have almost 0% efficiency compared with normal antennas, and we would just waste all the power just for heating the water from the power amplifier, not transmitting actually anything. The other thing is that even when using very low frequencies, the bandwidth is very limited. And as I said, we need some bandwidth to stream the image from the camera. So that's why we need to use some wired connection. And the first idea is that comes to mind is to use the Ethernet connection. It's easy to set up, it's reliable, it's cheap, it's well known. But it has a significant drawback that the Ethernet cables are rigid. They are very rigid, and especially when we have the power supply cable, which needs to carry 30 amps of current and have negligible voltage drop across it. This power also needs to be quite thick, and when we have the Ethernet cable, the whole cord is so stiff that it can alter the forces that are applied to the robot and make the maneuverability even harder, even worse than without this cable. So that's why we thought about other solution, and we use the optical fiber because the optical fibers are also cheap and quite easy to use, and they are much more flexible, much thinner. Their thickness is negligible compared with the power supply cable thickness. And since we can't do anything with the power supply cable, we need it to be thick, so we want to reduce the thickness of the other wire. And the main point of this presentation is to talk about the embedded system. So the question is, where is the embedded system and why is it needed? We must notice that we have some computer on the control station because there is an operator. The operator has a game controller to control the robot. The operator also needs to see the image from the camera, the view from the camera. So there is a computer that receives packets through the optical fiber. And see the view and control the robot. So we need another computer on board of the robot actually, because we need to receive the packets and then convert the bits in the packet to actual electrical signals that control motors or servos or other stuff. But the problem with the computer on board is that it takes space, and we have very limited space on board because we have just one box or one tube on our robot. We want it to be small and light. Also, the PC produces heat, and we have a lot of heat already on board because there are power converters, there are speed controllers for thrusters, and there is quite hot inside. So we want to move the computer from the robot itself to control station, so that we can move some algorithms that would be normally running on the robot, like the thrust allocation or some PID controlling, and move them to control station, because why not? But then if we get rid of the computer on board, we still need to have some translator that will translate the packets to actual electrical signals, and that's where the embedded system comes to play, because it's relatively easy to set up, it's very robust and cheap. I call it the executive embedded system because it basically executes its commands on the actual hardware. What do we have on board? This is the diagram of the elements of our robot. It's focused on embedded system, of course. In the center we have the embedded subsystem board based on STM32H745. This is a board with the MCU and some other elements around it. It's the core of the whole embedded system. From the left side you can see it's connected using the Ethernet bus to the Ethernet fiber converter, because we need to convert fiber to Ethernet to connect to camera and to connect to the embedded system. From the other sides we have the measurement inputs. We need to control the temperature and current of the power converters, which is the very important block here, because it supplies all motors and servos, and it consumes almost all the power that is supplied to the robot. It generates also a lot of heat, so we need to have some control over it. As you can see, we also have servos and HRS, AHRS, which is the positioning sensor that needs bidirectional communication, so reading some acceleration data and setting some configuration to the device, and the, let's say, protocol translation or gatewaying is done by the embedded subsystem. Why this MCU, the STM32H475? Because there is a Nucleo board with this MCU. This Nucleo board has built-in Ethernet PHY with Ethernet connector, so that we can get rid of all this cable mess when we have external modules, Ethernet modules, and which introduce some voltage drops across the cables, some interference, and we don't want that. So we have one elegant solution, one self-contained board. Also, we can have a few of these boards, and I can give these boards to the team members, and they can work using this board on the project in their homes. The MCU itself also features dual core. It's a dual core unit. It has, we don't use the second core actually for now, because the system is relatively simple, but in the future we'll see. The MCU also has multiple PWM outputs and ADC inputs, and we need plenty of them because we need to control the thrusters and servos with PWM, and also read temperatures and currents from all power converters, so that's why we need the ADC for. Also, this board has been used in our previous projects, I believe in all previous projects, so we still have plenty of these boards laying around, and it's just fine for its job. Okay, so the question is, what are the embedded system tasks? So as I said earlier, the most important task is the providing the abstraction or translation between the data packets and the electrical signals, because the control station may send a signal to set thruster free to 30% of its power, but it has no idea how the thruster is connected and what is PWM. So the embedded system's job is to get this input packet, then the embedded system knows where the motor is connected and how to apply 30% of duty cycle to the PWM output. The same thing is with servos, because they're also controlled by PWM. And with sensors like temperature and current, we have the ADC, so we get the request from the control station to measure the temperature of say, power converter 2, and the embedded system knows when the thermistor is connected, and it can read the voltage, convert it to degrees Celsius, and return the data to the control station. And with IHRS is the protocol gatewaying between UART and the Ethernet. The other important task is to provide an interactive motor power control. It's because the power supply that we use and the power supply that is provided by the competition hosts is the 48 volt 30 amp power supply, and that's slightly less than 1.5 kilowatt. And the motors we use on board of our robot are the 400 watts, and we have 6 of them, so it's almost 2.5 kilowatt. So we just can't run all the motors at the full power, because it will overload the PSU and it will just turn off, and we don't want that on the competition. So if we have such a case that we have some motors, the motors are running on some power, and they are already consuming all 1.5 kilowatt of power, and then we receive a request to set one motor's power to the higher level. So then we know that we will reach the threshold. We know that we will overload the power supply. So that's why we want to introduce some power control that we can proportionally decrease the power of all motors and then increase the power of this one motor, so that that the force vector that's applied to the robot will remain the same. We have the same direction, but will be just proportionally scaled, so the robot will be just swimming slower. The other important thing is balancing power converter load. Since we have the 48 volt 30 amp power supply, and the motors have a nominal working voltage of 16 volts, we need to decrease the voltage 3 times, so it also yields 3 times the current. So we have almost 100 amps for the motors. We can do that with one power converter. We need a few of them. And initially we have some motors connected to some power converters. And if we have a situation like there are 2 motors that are running on their full power or at a very high power, and they are connected to the same power converter, we would rather disconnect one motor and connect it to the other power converter, which is less loaded or not loaded at all. So we can do this kind of balancing power converter load, just to make sure that the power converters won't fail, and we won't fall out of the safe operating levels. And the last things are the fast over temperature and over current protection. Because we in theory you could measure the current, we could measure temperature, then gather all this data, send it to the control station, and wait for the control station to respond to some over temperature event, for example. But it takes time, and we want it to be fast. We wanted to have some mechanisms that will allow us to disable some systems immediately when some failure is detected. If we detect that there is over temperature, we could, for example, lower the power or disconnect something immediately. And we want the whole system to react fast. And with the control station embedded loop, it's slower. So that's why we would like to have it built in the embedded system. The last thing is the failure detection. When we detect that, for example, we set a motor power to some non-zero level and we still read 0 amps that 0 amps are drawn from the power converter, we know that something is wrong, that either the converter is broken or the motor controller is broken, and we want to notify the control station of such event. This is the firmware design diagram. It is actually the modules that we have in our firmware. On the right side we have the drivers that directly communicate with, that directly issue some electrical signals or read electrical signals. So you have PWM driver for motors and servos, the UART driver, the bidirectional driver for IHRS, the ADC driver for temperature and current measurement for now, and maybe for other sensors also, and the GPIO driver for standard push-pull outputs for controlling power converters and maybe some lights or other stuff. In the center we have the protocol stack, which is the core of the translator that encapsulates the data that come from the Ethernet, and then in this data we have some ID, and based on the ID we can transfer the payload to appropriate driver that knows how to parse the payload. On the left side we have the network stack, the TCP/IP stack, which is provided by the lightweight IP library, and the MAC Ethernet MAC driver, which is provided by the HAL. There is also one independent block, the control and protection logic block, that is responsible for controlling the power, this interactive power control, and also load balancing and failure detection. It also has a connection with the protocol stack, so it can notify the control station. As you can see, I named the block in the center as protocol stack or ROS node. So what is a ROS node? ROS is a robot operating system. It is a widely used platform, widely used framework actually, for writing the software for robots. What ROS does, it provides a way of uniform inter-process communication. So in ROS there is some core process that handles the communication, and we have separate processes for all modules that are called ROS nodes. So here is the example of such node, and the nodes communicate using a thing known as ROS topics. So the node can subscribe to a ROS topic and then receive the data associated with given ROS topic. All right, so what is the difference between the protocol stack and the ROS node? Because these are the two main approaches we consider in this build. So the ROS node is an elegant solution because we have our software which runs on the control station should use it, or at least should be using ROS. So all the modules like the trust allocation or PID controlling or the GUI controller GUI they all should be independent ROS nodes that communicate through the ROS framework. So I would like to have the ROS node as well in our embedded software, that it's there's another block of the whole system. But there are some problems. The ROS is written for Linux and runs on Linux exclusively, at least in its native version. We don't have Linux on our embedded system, so there is a way to connect this together. There is a port of ROS for microcontrollers known as micro-ROS. But it raises some compatibility issues because there are new versions of this full Linux ROS. I think they are newer than the current micro-ROS version, and I believe it might create some issues with interfacing all this together. And The other thing is possible implementation issues. We would need to integrate rows into our current embedded firmware, which might not be very easy. On the other hand, we might have the protocol stack, which was our first idea. The similar approach was used in our previous projects. So we just defined a packet format that we use for controlling our robots. So there was a module ID, some payload length, and the payload, which was dependent on the driver. And we have this protocol implemented on both sides, on the controlling software and on the embedded side. It was UDP based for simplicity, because with TCP you need to worry about all this TCP disconnection detection. When the connection is broken, it can take some time for the error to be detected. And you need to have some server and client the client needs to connect to the server, and we would rather just want to send the packet and hope that it reaches its destination. It's a good starting point for early iterations, for earlier versions, because it's easier to debug, easier to work with, especially when we just want to have our robot working with very basic capabilities, with very basic tasks, like just turn on some thrusters, and that's all. That we would use the protocol, our own protocol, because it's easy to debug. We can, for example, open the Wireshark and then analyze the packets. But of course, we need to integrate, at least in the next versions, you will need to integrate into the ROS, this ROS ecosystem to other ROS nodes. So we need to have the ROS node anyway. But the idea is that we can just push the ROS node up to the control station and make the ROS node the translator between the ROS framework, the ROS topics, and our own protocol stack, because it should be easy to do. The protocol stack works with standard Unix-like sockets, which are available on Linux, on Windows, on lightweight IP library, so that should be easy to implement. Of course, the micro-ROS solution is more elegant, but we'll see in the future. So that's all. Thank you for your attention. And if you have any questions, I will try to answer.
Thanks for presentation. I have few questions about the architectural decision you have taken. Why did you decide to use these micro ROS, not, for example, FreeRTOS, which is quite of native for STM?
Yes, it's called ROS, but it's not an operating system. There is no scheduler, no things like that. It's called ROS. I don't know really why, but it's just a framework that facilitates the inter-process communication, basically. And I believe the ROS actually runs on RTOS. We need RTOS to run ROS because it forms some process on RTOS and integrates into RTOS.
Okay, and second question is about the custom communication protocol which you have created between this vehicle and also control station. Have you thought about using something standard like MQTT, for example, or not really?
Maybe not for now.
Okay. And last question from control theory, let's say. You've mentioned that you have PID controller on this main station, is it correct?
Not yet, but we want to have it.
Okay, so when you have it, how you deal with delays which you will have between sending and receiving signal, because TCP/IP is non-deterministic, so you don't know what are the delays, and they will differ.
Yes, It's hard to say for me right now. I don't know if we'll be using the PID controller at all, because the operator is kind of a controller in such scenario, because the operator sees the view from the camera, and then the operator makes some decisions on how to control the robot. So I don't know if we really need it, especially that the PID controllers have problems with accumulating error when we are using AHRS, which just provides us the acceleration data, and we need to calculate the velocity, and the error accumulates. So for now, we are focusing on building a very basic version of the robot, just to make it to turn on the engines, to turn on the thrusters, and make it swim a little bit.
Thanks. Hello, I've got a couple of questions as well. First of all, you've shown on the architecture diagram that you have this converter between fiber and Ethernet, and behind that there is the embedded subsystem and there is the camera. Does that mean that the camera is a completely separate device with a separate IP address and all that, right?
Yes.
Okay.
I don't. It has some IP, but it's quite complicated because there is some SDK made for the camera, and I don't know. I haven't found anything about like a standard streaming protocol that we can use to get the view from the camera, the image from the camera, but it must have some IP.
Okay. The next question actually kind of relates to one of the other questions that was asked. Are you using some kind of RTOS? And if so, what kind of RTOS is it? Or are you just writing it completely bare metal?
Some of you would probably want to kill me, but no, for now we don't have any kind of RTOS. For now, maybe in the future it will change, but it was my decision to write everything bare metal for now, because I came to a conclusion that we just want to do everything in the best effort manner, because we don't really need to have anything real time. We just want to minimize the delays, maybe not really care about the jitter, but rather minimize the delays.
Okay, so the last question is, you said that this microcontroller that you are using is dual core. Are you using both of the cores, and if so, how?
No, as I said, we are not using the second core right now. We are using just the one core. It has M7 and M4 cores, but we are using the first one.
Okay, thank you.
Since it's after hours project for most of you, I believe, what's the estimated timeline for design of such device?
Do you mean the embedded system or the whole robot?
The whole robot.
The competition is in July, so we hope that we will do it up to this day. But
So when did you start? When you hope to finish in July?
The beginning of this academic year, so around September, October, something like this.
Okay. Good luck. Sounds impressive.
Thank you.
Okay, if I understand correctly from some other slide where you had this diagram, the communication between the device, this robot and the control station is based on TCP/IP. Why TCP/IP and not UDP, which would be easier and faster?
Yeah, I wrote TCP/IP as the whole family of these protocols, but we are using UDP.
Okay.
A very non-technical question. So, what will be the most unique point of this product? Like, what is more like the unique thing about this product? When you compare it with the other competitors.
Maybe this is a student project, so we just want to attend the competition and probably win the competition. But the thing is that there are only 2 or 3 such clubs in Poland, or even one other club that specializes in underwater robotics. So it's quite unique if we think about it, because the clubs that are building different kinds of robots, for example, some maybe not just other robots. There are a lot of clubs that do robots, but the underwater robotics is a very unknown and unpopular topic.
Okay, thank you.
Any more questions? Okay, thank you so much. So we are done with the official part for today. I welcome you to stay for some beer and pizza in a second, I hope. Yes, and thank you for attending.